Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 15. We are discussing about how to prepare different molds, and so typically the molds are made by hand if they are very small in number. Obviously if you want to build one component or maybe about close to probably 10 components, still it is economical that you make the molds mostly by ramming or squeezing the sand by preparing the cope half and drag half separately and trying to now match them together. So, this whole thing can be a hand operation by the molder, but if larger number of simple molds are needed, then obviously for the yield purposes molding machines have to be used. For example, if you are talking about a casting industry which produces, let us say at the rate of probably 50,000 castings a day of small parts. Okay, so there every time making these kind of intricate molds is not a possibility, and as you know, it has to be a rigorous process of aligning a pattern to the cope and drag half of a casting, and for each and every part if such a process is executed manually, it is going to take a large amount of time. So, obviously you have to automate the process and you have to see how in a better manner the sand can be thrown or slinged or slammed or whatever, and the process has to be fast so that it can produce the patterning of the sand at a higher rate. So, we want to discuss some of the important features of the mold making process which are normally used for making the system handle better or handle easily the metals in liquid state. So, one of them is using of this parting compound, which is also known as the mold release agent. The idea is that you should be able to distinguish after removal of the frozen metal piece, you should be able to distinguish the mold half or the mold surface properly with respect to the piece which you are removing, and so for doing that you need a parting compound which is normally some kind of a talc powder. It is like a non-wetting talc powder which is a dry dust and which is sprayed with an intention that whatever absorption, whatever moisture was there within the mold, part of it is absorbed and it formulates a layer, a parting layer on the surface where it immediately gets dried up and gets loose, so that it releases the surface and the metal does not have to formulate some kind of a bondage with material on the surface. So, the mold breakage will not be there and you can actually be able to remove the frozen material properly. So, it is normally dusted, this talc is dusted on a pattern before actually doing the molding. So, it will also ensure a sort of a finer grain facing by going into the voids etcetera of the surface, because it is loose dust and so it can go into the voids easily. It is smaller in size than the voids between the sands, and so you can have a smoother surface rather than a rough surface because of the distributed voids within the top of this sand casting. There is also the requirement of a dead weight which sometimes is placed on the cope flask, as you can see here in this particular illustration. It is a 3-part mold they are saying. So, there is a dead weight on the top. So, these are normally provided to avoid the floating because of buoyancy forces or hydrodynamic forces as the metal enters the mold. Obviously, if even if the cope half is smaller in comparison to the drag half, as I had discussed before, there is a tendency that the floating the liquid metal getting into a high pressure may able to float up the cope with respect to the drag because of the hydrodynamic forces. Okay. So, in order to stop that, it is better that you always put a dead weight on the top of the cope half, so that it remains intact and it manages to stay back in position instead of all these hydrodynamic forces available. So, a dead weight is normally placed. Okay. For a larger mold, care should be taken to prevent the sand from falling off the cope flask when it is lifted, and that is mostly to remove the pattern. It should not happen that you have the pattern in place and the sand is nicely holding. The moment you try parting the upper half, the sand starts falling back. So therefore, the pattern gets damaged or lost. So you have to have enough pressure and you have to have the enough percentage of the water vis-a-vis the sand and the clay, as I illustrated just in my earlier module, so that it can hold and constitute a integrated surface, which is exactly the negative of the pattern in place. So it can be provided extra supports, and these are sometimes known as gaggers, and which is normally provided within the cope flask to ensure that there is no fall of the sand, loose sand, thus damaging the overall pattern surface in the cope half. The other purpose of a gagger is basically because if the casting size is too large, then maybe the sand is unable to hold such a weight of the sand over the whole cope half, and therefore additional supports etc., which may be of the same metal as you are casting, has to be made. So the idea is when the metal comes and fills up, obviously this metal is going to melt away into the parent metal mix, which was otherwise holding the sand cavity in place. But then if it mixes, then again the hydrodynamic forces come because it is in liquid state, and so it will like to still be compressing the mold on all sides, and that hydrodynamic force set would keep it stabilized after the liquid metal is poured. So the purpose of a gagger is only from the point of time that the patterning has been done to the point of time that the liquid metal reaches the mold cavity. So you can also have re-entrant surfaces for casting, and that is why casting is normally carried out in 3 parts. As you can see here, this big wheel being casted. So there is an upper half here which actually is in the cope half. You can see this particular half has been designed to hold the pattern in the cope half, and you can see this surface here which is really not there in the original pattern, and it is a re-entrant surface. Okay. So this surface is basically preventing the metal from flowing out, so that this cross section of the wheel can be obtained. It is a circular pattern that we are talking about in this particular case. Okay. And so this shape is only obtained because you give additional sand, re-entrant sand here once the patterning has been done, and it will prevent the metal from going into this place. Okay. So such parts are also available, and so you use now 3 parts of the mold, and normally the name of the middle part is the cheek. Okay. So you have the cope half, the drag half and the cheek, all 3 clamped together. So you have to ensure this clamping arrangement also to prevent the cheek from moving up because of the hydrodynamic forces etc., moving out because of the hydrodynamic forces etc. You have to provide escape route for the gases by vent holes, and these are normally provided in the cope half, cope flask, so that from time to time you can withdraw the gases which are soluble otherwise in the metal. And let us now talk about a little bit high throughput production process of the mold. So typically there are different techniques like jolt ramming. You can see this is the the cope half, drag half assembled together with sand, and you have poured sand over it, and you are basically trying to pick up the mold and jolt it by giving a rectilinear motion, to and fro rectilinear motion here to this surface, so that the sand settles down. So by changing the momentum of the sand from time to time, you ensure that the sand compresses with respect to each other. And there can be other methods, high throughput methods of doing sand molding. For example, you put the sand and squeeze, so this can be an automated system which can do the squeezing action over several molds at a single point of time. Even this can be an automated system where the whole cast is basically put with all the sand and jolt rammed, so that the sand can settle down. There are slingers which are even able to increase the throughput further, where basically sand is thrown at a high pressure, so that it can go and sit on the top of the the cope and drag and sit on top of the pattern. So in jolt ramming, the mold is lifted through a height of about 5 centimeters and dropped 50 to 100 times at a rate of 200 times per minute. Some uneven ramming is there, but it is quite suitable for horizontal surfaces. For shallow flask kind of orientations, squeezing is found to be a high throughput alternative, and sand slinging operation is mostly when there is a uniform ramming requirement which is there of the whole sand. So, apart from that, obviously the process of separating the cope and the drag half and releasing the pattern has to be automatic. So, in large foundries this is how things are normally made. Let us now look into another aspect, which is melting. So, obviously we have now prepared the sand mold, we have also prepared different kind of patterns, we have integrated the patterns onto the sand mold, formulated a cavity, given a riser and a runner, and also the gate and pouring basin. So, now the next question is that you have to melt the material, so that it can come to the liquid state and flow into the mold cavity. So, a proper care needs to be done during melting. It is essential for good and defect free casting. The factors that are to be considered for melting include gases in metals. This is a very important constituent. Hydrogen, for example, makes iron go very brittle. So, as low solubility as possible would be advisable when you are talking about making perfect or high high strength castings. Then the selection and control of the scrap is very important. Obviously, flux, the furnace and the temperature, which can release a lot of gases because of remnants of oil, etc., that is also very important in this case. And so, typically what do gases do? So, gases in metals normally lead to, as I told you, faulty castings. However, the presence of a controlled amount of a specified gas can be beneficial, particularly in imparting certain desirable qualities of the casting. How do metals or how do gases get trapped into the metals? Again, if you had no proper venting arrangements for the gases, the first trapping that may come is mechanical trapping, because obviously there are going to be some hydrocarbons or oil within the furnace which is going to generate this gas, and the liquid has a certain solubility, and there are a classification of materials based on whether they are endothermic or exothermic, where the solubility may vary with the temperature in a non-identical manner. And for example, as regards the group which is called endothermic metals, they may include metals such as aluminum, magnesium, copper, iron and nickel, and exothermic metals may include others like titanium and zirconium. Okay. So, the difference here is obviously in terms of what happens to the solubility of the gases into these materials at higher temperatures or maybe during cooling situations. So, mechanical trapping is one aspect. Okay. So, because of bubbling of the hydrogen and not letting it vent out very easily. There can be also a case where, let us say, two different metals are being casted as an alloy, and there is a variation in the solubility of gas phase in one of the metal systems, and it actually suddenly outgasses because of change in temperature, and the gas does not have any other way to go but to get trapped within the material. And then obviously there can be chemical reactions between the gases and some phases of the material, which may lead to again embrittlement of the material. Okay. So, these are some of the ways that mechanical gases are kind of introduced within the casting, and the most common problems which are there in the casting of iron and steel are the two gases, hydrogen and nitrogen. Okay. And as far as metals are divided, as I told you, for the solubility of hydrogen you can divide them into an endothermic and an exothermic category. The only difference here is that if you look at the solubility equation, the solubility equation here S is related to some constant C times of exponential minus Es by k theta. Theta is the absolute temperature, and K is a constant related to the material. So, this is the absolute temperature. K is a constant related to the material, and C is also another constant, okay, again related to the material, and this Es here is really the heat of the solution for 1 mole of hydrogen. So, the Es is positive for the endothermic materials. So, therefore, if supposing theta were to increase, I am saying S equal to C exponential minus Es by k theta. So, if theta were to increase and Es is positive in this particular case, so obviously the solubility is going to go down as you are going higher in temperature, and the solubility would be more as the temperature goes down, okay, because now C by exponential Es by k theta, this term here as the theta goes down would increase and the solubility goes down as the theta goes down also. Okay. So, there is no problem that in such cases the gases are going to get outgassed obviously, because from the freezing temperature of the casting you are going to room temperature, and in the process of doing that you are taking the temperature down. Okay. So, as the temperature is going down, the solubility of the gases are also going to reduce, as you can see here from this plot. However, if this Es were negative, which is the case of the exothermic materials, the problem starts happening, okay, because now because of the negative Es value, the decrease in the temperature may actually result in an increase in the solubility. Okay. So, and obviously in such materials like exothermic materials, as the Es value is negative, the solubility here will be C exponential Es by k theta, and if theta decreases in this particular case, obviously this exponential factor is going to increase and the solubility is going to increase. So, if the temperature comes down in exothermic materials, the solubility of the gas is going to increase. Okay. So, that is a problem, because the gas cannot be precipitated anymore. So, where does the gas go? So, it formulates small pockets, small voids within the materials, imperfections, and such exothermic materials, it is very difficult to actually do the casting process, and you will have to somehow be able to play around with the solubility by making some additives or something, so that the gases can start coming out. Okay. So, hydrogen is why it is so detrimental to the particularly the exothermic materials, is that actually it dissolves interstitially within the exothermic material. So, it causes a lot of mechanical energy, a lot of stress within the lattice by distorting the lattice, by getting into the interstitial sites, and so it is a sort of a defect that you are introducing into the metal by adding a hydrogen species everywhere within that lattice site. Okay. So, the lattice gets pre-stressed because of it, okay. And that is why it is not a very good idea to have hydrogen into play, particularly with the exothermic materials where the solubility is going up with the reduction in temperature. So, you can see this table here, the solubility of hydrogen in various metals corresponding to 1 atmospheric pressure, and you can see that for iron, although the liquid solubility is 270 cubic centimeter per kg, the solid solubility is about 70. Okay. Similarly, in magnesium it is 260 and 180, in copper it is 55 and 20, aluminum it is 7 and 0.4, and this brings a problem that particularly in the liquid state, if the solubility is high of the material, and in the solid state the solubility is low, therefore, where is this gas going to go if supposing the material is exothermic in nature? Okay. So, obviously, it is going to be there as gas pockets, because now it has not been it has been shelled out of the material, and it cannot go because the solidification rate is quite fast, and there is going to be formulation of gas pockets. So, that is how solubility is very, very important from melting perspective when we talk about castings. Okay. And in a way, the other important factor here which would like to see is that if you look at is there a quantification of the percentage hydrogen present as a function of the partial pressure of the hydrogen which is around. So, this is actually given by the Sievert's law, which states that the percentage hydrogen present is basically proportional to the partial pressure of hydrogen to the power of half, and this is actually the partial pressure of the hydrogen in the atmosphere over the melt. So, when you are melting this iron in a furnace, and there is some hydrogen pressure which is there, it actually determines what is the percentage solubility or what is the percentage dissolution within the species. Okay. So, the constant K actually can be evaluated from table 2.2, where you can see the solubilities S to be given in iron, and so with that you can evaluate with different, like if the partial pressure is 1 atmosphere and the percentage present is some x cc per kg as a percentage, then the K obviously is going to be the value in cc per kg, as a percentage of the hydrogen present. So, you can calculate the table, or you can, from the table you can calculate this K value for the various metals, assuming 1 atmosphere partial pressure of hydrogen. The primary sources of hydrogen in the melt are furnace dampness, air and oil. I think I have mentioned this already. So, you have a lot of excess oil or air or dampness or even grease, and this can actually, these are hydrocarbons, they can generate hydrogen and carbon dioxide, and these two can then get added into the melt. There is no simple dehydrogenation addition to eliminate hydrogen in the form of slag. That is another big problem. So, you have to really when in case of hydrogen avoid formulating at the first place, because you can't remove it as a floating slag layer, you know. So, and the partial pressure of hydrogen can be reduced by bubbling some other dry insoluble gases, and that is the only way where you can actually reduce the partial pressure. And for non-ferrous metals, things like chlorine, nitrogen, helium or argon is very frequently used, so that the hydrogen partial pressure drops down and the solubility or the percentage of hydrogen present also drops down. So, overall you can have a good situation with less as possible of hydrogen in the casts. For again ferrous and nickel materials kind of based alloys, you cannot use nitrogen because they may formulate again nitrides, which are not very conducive for the strength aspect of the castings, and it may generally affect the grain size. Also, because grain size is an important mechanical property which brings out the strength aspect of the material. Generally a better procedure is to avoid the formulation of nitrides, so that the strength can be reasonably controlled. So, there is an increasing trend in the industry of doing vacuum melting nowadays. So, you do not really bother about the various gases, because you have outgassed the furnace before you have started the melting process, and so this is being increasingly used, although it is expensive, and it has to really be a smaller furnace, and it cannot be applied to a very large scale melting process, because vacuuming a certain region becomes very expensive. But there is a increased utility of vacuum based melting methods for producing melts. So, I would like to end on this module here, but in the next module we will look at some of the furnaces and then start designing some real castings with making the dimensions of the cavity, the runner, the time of flow of the materials, so on and so forth. Thank you so much.